Development of Earth. The advancement of this planet and its environment led to life, which molded Earth's resulting improvement. Our future lies in deciphering this geologic past and thinking about what changes, great and terrible, may lie ahead. Like the lapis lazuli pearl it takes after, the blue, cloud-wrapped planet that we perceive quickly from satellite pictures appears surprisingly stable. Continents and seas, enclosed by an oxygen-rich environment, support natural living things. However, this consistency is a dream created by the human experience of time. Earth and its environment are persistently changed. Plate tectonics move the mainlands, raise mountains and move the sea depths, while measures not completely comprehended change the environment. Such steady change has described Earth since its starting some 4.5 billion years prior. From the beginning, warmth and gravity formed the development of the planet. These powers were progressively joined by the worldwide impacts of the rise of life. Investigating this previous offers us the solitary chance of understanding the root of life and, maybe, its future. Researchers used to accept the rough planets, including Earth, Mercury, Venus and Mars, were made by the fast gravitational breakdown of a residue cloud, a diation leading to a thick circle. During the 1960s, the Apollo space program changed this view. Investigations of moon cavities uncovered that these gouges were brought about by the effect of particles that were in extraordinary bounty about 4.5 billion years prior. From there on, the quantity of effects seemed to have immediately diminished. This perception revived the hypothesis of accumulation proposed by Otto Schmidt. The Russian geophysicist had proposed in 1944 that planets filled in size continuously, bit by bit. As per Schmidt, inestimable residue lumped together to frame particulates, particulates became rock, rock turned out to be little balls, at that point enormous balls, at that point small planets, or planetesimals, and, nally, dust turned into the size of the moon. As the planetesimals increased, their numbers diminished. Therefore, the quantity of impacts between planetesimals, or shooting stars, diminished. Less things accessible for gradual addition implied that it required some investment to develop an enormous planet. A count made by George W. Wetherell of the Carnegie Institution of Washington recommends that around 100 million years could pass between the arrangement of an article estimating 10 kilometers in distance across and an item the size of Earth. The cycle of accumulation had huge warm ramifications for Earth, outcomes that strongly coordinated its development. Enormous bodies hammering into the planet delivered gigantic warmth in its inside, softening the vast residue discovered there. The subsequent heater, arranged nearly 200 to 400 kilometers underground and called a magma sea, was dynamic for a long period of time, bringing about volcanic ejections. At the point when Earth was youthful, heat at the surface brought about by volcanism and magma OWS from the inside was strengthened by the consistent assault of enormous items, some of them may be the size of the Moon or even Mars. No life was conceivable during this period. Past explaining that Earth had shaped through accumulation, the Apollo program constrained researchers to attempt to recreate the resulting transient and actual improvement of the early Earth. This endeavor had been viewed as unthinkable by organizers of geography, including Charles Lyell, to whom the accompanying expression is credited: no remnant of a start, no possibility for an end. This assertion passes on the possibility that the youthful Earth couldn't be remade, on the grounds that its leftovers were obliterated by its actual movement. However, the advancement of isotope geography during the 1960s had delivered this view old. Their minds read by Apollo and the Moon NDINGS, geochemists started to apply this method to comprehend the development of Earth. Dating rocks utilizing supposed radioactive tickers permits geologists to chip away at old landscapes that don't contain fossils. The hands of a radioactive clock are isotopes, molecules of the very component that have diverse nuclear loads, and geologic time is estimated by the pace of rot of one isotope into another. See The Earliest History of the Earth, by Derek York. Scientific American, January 1993. Among the numerous timekeepers, those dependent on the rot of uranium-238 into lead-206 and of uranium-235 into lead-207 are unique. Geochronologists can decide the time of tests by investigating just the little girl item, for this situation, lead of the radioactive parent, uranium. Searching for gold geology has allowed geologists to verify that the growth of Earth finished in the separation of the planet, the formation of the center, the wellspring of Earth's attractive field and the start of the air. In 1953, the exemplary work of Claire C. Patterson of the California Institute of Technology utilized the uranium lead clock to build up a time of 4.55 billion years for Earth and a large number of the shooting stars that framed it. In the mid-1990s, notwithstanding, work by one of us, Allegra, on lead isotopes prompted a fairly new translation. As Patterson contended, a few shooting stars were without a doubt framed about 4.56 billion years prior, and their trash established Earth. However, Earth kept on developing through the assault of planetesimals until somewhere in the range of 120 million to 150 million years after the fact. Around then 4.44 billion to 4.41 billion years prior, Earth started to hold its climate and make its center. This chance had effectively been recommended by Bruce R. Doe and Robert E. Zartman of the U.S. Geographical Survey in Denver 20 years prior and is in concurrence with Wetherell's gauges. The rise of the mainlands came fairly later. As indicated by the hypothesis of plate tectonics, these landmasses are the solitary piece of Earth's outside layer that isn't reused and, thusly, annihilated during the geothermal cycle driven by the convection in the mantle. Landmasses consequently give a type of memory on the grounds that the record of early life can be perused in their stones. Geologic action, notwithstanding, including plate tectonics, disintegration and transformation, has obliterated practically every one of the antiquated rocks. Not many pieces have endured this geologic machine. By the by, in late many years, a few significant NDS have been made, again utilizing isotope geochemistry. One gathering, driven by Stephen Morbath of the University of Oxford, found territory in West Greenland that is between 3.7 billion and 3.8 billion years of age. Also, Samuel A. Bowring of the Massachusetts Institute of Technology investigated a little region in North America, the Acasta gneiss, that is believed to be 3.96 billion years of age. At last, a journey for the mineral zircon drove different analysts to significantly more antiquated landscape. Commonly found in mainland rocks, zircon isn't disintegrated during the interaction of disintegration yet is stored in molecule structure in silt. A couple of bits of zircon can accordingly make do for billions of years and can fill in as an observer to Earth's more antiquated hull. The quest for old zircons began in Paris with crafted by Annie Vitrac and Joel R. Lancelot, later at the University of Marseille and now at the University of NMEs, separately, just as with the endeavours of Morbath and Algae. It was a gathering at the Australian National University in Canberra, coordinated by William Compston, that was nally fruitful. The group found zircons in Western Australia that were between 4.1 billion and 4.3 billion years of age. Zircons have been significant not just for understanding the age of the landmasses yet for deciding when life RST showed up. The most punctual fossils of undisputed age were found in Australia and South Africa. These relics of blue-green growth are about 3.5 billion years of age. Manfred Szydlowski of the Max Planck Institute for Chemistry in Mainz considered the Isua development in West Greenland and contended that natural matter existed as quite a while in the past as 3.8 billion years. Since the greater part of the record of early life has been annihilated by geologic movement, we can't say precisely when it RST showed up. Maybe it emerged rapidly, perhaps even 4.2 billion years prior. Stories from gases. One of the most significant parts of the planet's development is the arrangement of the climate, since it is this collection of gases that permitted life to creep out of the seas and to be maintained. Analysts have estimated since the 1950s that the Earth-bound climate was made by gases arising out of the inside of the planet. At the point when a fountain of liquid magma heaves gases, it is an illustration of the persistent outgassing, as it is called, of Earth. Be that as it may, researchers have addressed whether this cycle happened unexpectedly, about 4.4 billion years prior when the center separated, or whether it occurred steadily over the long haul. To address this inquiry, Allegre and his associates contemplated the isotopes of uncommon gases. These gases, including helium, argon and xenon, have the eccentricity of being synthetically inactive, that is, they don't respond in nature with different components. Two of them are especially significant for climatic investigations: argon and xenon. Argon has 3 isotopes, of which argon-40 is made by the rot of potassium-40. Xenon has 9, of which xenon-129 has 2 unique birthplaces. Xenon-129 emerged as the aftereffect of nucleosynthesis before Earth and nearby planetary group were framed. It was additionally made from the rot of radioactive iodine-129, which doesn't exist on Earth any longer. This type of iodine was available almost immediately yet has ceased to exist since, and xenon-129 has developed to its detriment. Like most couples, both argon-40 and potassium-40 and xenon-129 and iodine-129 have stories to tell. They are great chronometers. Albeit the environment was framed by the outgassing of the mantle, it doesn't contain any potassium-40 or iodine-129. All argon-40 and xenon-129, framed in Earth and delivered, are found in the environment today. Xenon was ousted from the mantle and held in the climate. Along these lines, the air-mantle proportion of this component permits us to assess the period of separation. Argon and xenon caught in the mantle advanced by the radioactive rot of potassium-40 and iodine-129. Subsequently, if the all-out outgassing of the mantle happened toward the start of Earth's arrangement, the environment would not contain any argon-40, however would contain xenon-129. The significant test confronting an examiner who needs to gauge such proportions of rot is to get high centralizations of uncommon gases in mantle rocks, since they are very restricted. Luckily, a characteristic marvel happens at mid-sea edges during which volcanic magma moves a few silicates from the mantle to the surface. The limited quantities of gases caught in mantle minerals ascend with the dissolve to the surface and are gathered in little vesicles in the external smooth edge of magma OWS. This cycle serves to focus the measures of mantle gases by a factor of 104 or 105. Gathering these stones by digging the SEAOOR and afterward smashing them under vacuum in a delicate mass spectrometer permits geochemists to decide the proportions of the isotopes in the mantle. The outcomes are very astonishing. Computations of the proportions demonstrate that somewhere in the range of 80 and 85% of the air was outgassed during Earth's RST 1 million years. The rest was delivered gradually, however continually during the following 4.4 billion years. The organization of this crude climate was unquestionably overwhelmed via carbon dioxide, with nitrogen as the second most bountiful gas. Follow measures of methane, alkali, sulfur dioxide and hydrochloric corrosive were likewise present, however there was no oxygen. Aside from the presence of bountiful water, the environment was like that of Venus or Mars. The subtleties of the advancement of the first climate are discussed, especially in light of the fact that we don't have the foggiest idea how solid the Sun was around then. A few realities, notwithstanding, are not questioned. It is obvious that carbon dioxide assumed an essential part. Moreover, numerous researchers accept the developing climate contained adequate amounts of gases like alkali and methane to bring about natural matter. All things considered, the issue of the Sun stays uncertain. One theory holds that during the Archean age, which endured from about 4.5 billion to 2.5 billion years prior, the Sun's power was just 75% of what it is today. This chance raises a quandary. How could life have made due in the moderately cool environment that ought to go with a more vulnerable Sun? An answer for the weak early Sun Catch-22, as it is called, was offered via Carl Sagan and George Mullen of Cornell University in 1970. The two researchers proposed that methane and alkali, which are extremely powerful at catching infrared radiation, were very bountiful. These gases might have made a super-nursery impact. The thought was reprimanded on the premise that such gases were exceptionally responsive and have short lifetimes in the climate. What controlled In the late 1970s, Veerabhadran Ramanathan, presently at the Scripps Institution of Oceanography, and Robert D. Sess and Tobias Owen of Stony Brook University proposed another arrangement. They proposed that there was no requirement for methane in the early environment since carbon dioxide was sufficiently bountiful to achieve the super-nursery impact. Again, this contention brought up an alternate issue: how much carbon dioxide was there in the early air? Earthly carbon dioxide is currently covered in carbonate rocks, like limestone, in spite of the fact that it isn't clear when it got caught there. Today, calcium carbonate is made essentially during organic movement. In the Archean age, carbon may have been basically taken out during inorganic responses. The quick outgassing of the planet freed voluminous amounts of water from the mantle, making the seas and the hydrologic cycle. The acids that were most likely present in the environment dissolved rocks, framing carbonate-rich rocks. The overall significance of such a system is, be that as it may, discussed. Heinrich D. Holland of Harvard University accepts the measure of carbon dioxide in the climate quickly diminished during the Archean and remained at a low level. Understanding the carbon dioxide substance of the early environment is significant to understanding climatic control. Two connecting camps have advanced thoughts on how this cycle functions. The RST bunch holds that worldwide temperatures and carbon dioxide were constrained by inorganic geochemical inputs. The second states that they were constrained by organic expulsion. James C. G. Walker, James F. Casting and Paul B. Ruffages, at that point at the University of Michigan at Ann Arbor, proposed the inorganic model in 1981. They hypothesized that levels of the gas were high at the start of the Archean and didn't fall abruptly. The threesome proposed that as the environment warmed, more water dissipated, and the hydrologic cycle turned out to be more fiery, expanding precipitation and spillover. The carbon dioxide in the air blended in with water to make carbonic corrosive spillover, uncovering minerals at the surface to enduring. Silicate minerals joined with carbon that had been in the air, sequestering it in sedimentary rocks. Less carbon dioxide in the environment implied, thusly, to a lesser extent a nursery impact. The inorganic negative criticism measure counterbalanced the increment in sun-oriented energy. This arrangement stands out from a subsequent worldview, natural evacuation. One hypothesis progressed by James E. Lovelock, an originator of the Gaia theory, expected that photosynthesizing microorganisms, like phytoplankton, would be beneficial in a high carbon dioxide climate. These animals gradually eliminated carbon dioxide from the air and seas, changing over it into calcium carbonate dregs. Pundits answered that phytoplankton had not developed for more often than not that Earth has had life. The Gaia theory holds that life on Earth has the ability to manage temperature and the structure of Earth's surface and to keep it agreeable for living organic entities. In the mid-1990s, Tyler Volk of New York University and David W. Schwartzman of Howard University proposed another Gaian arrangement. They noticed that microorganisms increment carbon dioxide content in soils by separating natural matter and by producing humic acids. The two exercises speed up enduring, eliminating carbon dioxide from the air. On this point, nonetheless, the contention gets intense. Some geochemists, including Casting, presently at Pennsylvania State University, and Holland, propose that while life may represent some carbon dioxide expulsion after the Archean, inorganic geochemical cycles can clarify the greater part of the sequestering. These analysts see life as a fairly feeble climatic balancing out instrument for the majority of geologic time. Oxygen from algae. The issue of carbon stays basic to how life annuanced the air. Carbon internment is a key to the crucial interaction of developing air-oxygen fixations, and essential for the improvement of certain living things. Likewise, an unnatural weather change is occurring now because of people delivering this carbon. For 1 billion or 2 billion years, green growth in the seas delivered oxygen. But since this gas is exceptionally responsive and in light of the fact that there were many diminished minerals in the old seas, iron, for instance, is effectively oxidized, a large part of the oxygen delivered by living animals just got spent before it could arrive at the environment, where it would have experienced gases that would respond with it. Regardless of whether developmental cycles had brought about more convoluted life structures during this anaerobic period, they would have had no oxygen. Besides, unlte red bright daylight would have likely killed them in the event that they left the sea. Specialists like Walker and Preston Cloud, at that point at the University of California at Santa Barbara, have proposed that just around 2 billion years prior, after the majority of the decreased minerals in the ocean were oxidized, did climatic oxygen aggregate. Between 1 billion and 2 billion years prior, oxygen arrived at current levels, making a specialty for developing life. By analyzing the solidness of specific minerals, like iron oxide or uranium oxide, Holland has shown that the oxygen substance of the Archean climate was low before 2 billion years prior. It is to a great extent concurred that the present-day oxygen substance of 20% is the consequence of photosynthetic action. In any case, the inquiry is whether the oxygen content in the air expanded bit by bit over the long run or abruptly. Ongoing investigations show that the expansion of oxygen began unexpectedly between 2.1 billion and 2.03 billion years prior, and that the current circumstance was arrived at 1.5 billion years prior. The presence of oxygen in the climate had another major benefit for a living being attempting to live at or over the surface: it lte red bright radiation. Bright radiation separates numerous atoms, from DNA and oxygen to the chlorofluorocarbons that are involved in stratospheric ozone consumption. Such energy parts oxygen into the profoundly insecure nuclear structure O, which can join once more into O2 and into the extremely uncommon atom O3, or ozone. Ozone, thus, assimilates bright radiation. It was not until oxygen was bountiful enough in the environment to permit the arrangement of ozone that life even got an opportunity to get a root hold or attraction ashore. It's anything but an incident that the fast development of life from prokaryotes, single-celled life forms with no core, to eukaryotes, single-celled creatures with a core, to metazoa, multi-celled living beings, occurred in the billion-year-long period of oxygen and ozone. Albeit the environment was arriving at a genuinely steady degree of oxygen during this period, the environment was not really uniform. There were long phases of relative warmth or coolness during the progress to current geologic time. The organization of fossil microscopic fish shells that lived close to the seafloor gives a proportion of base water temperatures. The record recommends that in the course of the last 100 million years base waters cooled by almost 15 degrees Celsius. Ocean levels dropped by many meters, and mainlands floated separated. Inland oceans generally vanished, and the environment cooled a normal of 10 to 15 degrees C. Approximately 20 million years prior, lasting ice seems to have developed on Antarctica. Around 2 million to 3 million years prior, the paleoclimatic record begins to show significant developments and constrictions of warm and cold periods in 40,000 year or so cycles. This periodicity is intriguing on the grounds that it compares to the time it takes Earth to finish a swaying of the slant of its hub of revolution. It has for some time been conjectured, and as of late determined, that known changes in orbital math could adjust the measure of daylight coming in the middle of winter and summer by around 10% or somewhere in the vicinity, and could be answerable for starting or finishing ice ages. The warm hand of man. Most interesting and puzzling is the disclosure that somewhere in the range of 600,000 and 800,000 years prior, the predominant cycle changed from 40,000 year time frames to 100,000 year stretches with enormous fluctuations. The last significant period of glaciation finished around 10,000 years prior. At its stature 20,000 years prior, ice sheets around 2 kilometers thick covered quite a bit of northern Europe and North America. Ice sheets extended in high levels and mountains all through the world. Enough ice was secured ashore to cause ocean levels to drop in excess of 100 meters underneath where they are today. Gigantic ice sheets scoured the land and patched up the environmental essence of Earth, which was VE degrees C cooler on normal than it is at present. The exact reasons for the more drawn-out spans among warm and cold periods are not yet figured out. Volcanic emissions may have played a significant job, as demonstrated by the impact of El Chichon in Mexico and Mount Pinatubo in the Philippines. Structural occasions, like the improvement of the Himalayas, may have a nuanced world environment. Indeed, even the effect of comets can nuance transient climatic patterns with calamitous ramifications for life. See, What Caused the Mass Extinction? An Extraterrestrial Impact, by Walter Alvarez and Frank Asaro. And What Caused the Mass Extinction? A Volcanic Eruption, by Vincent E. Cortio, Scientific American, October 1990. It is amazing that regardless of rough, rambling bothers, the environment has been adequately supported to support life for 3.5 billion years. Perhaps the most vital climatic revelations of the previous 30 years has come from ice centers in Greenland and Antarctica. At the point when snow falls on these frozen mainlands, the air between the snow grains is caught as air pockets. The snow is progressively packed into ice, alongside its caught gases. A portion of these records can return over 500,000 years. Researchers can dissect the substance of ice and air pockets from areas of ice that lie as profound as 3,600 meters, 2.2 miles, beneath the surface. The ice center drills have confirmed that the air inhaled by old Egyptians and Anasazi Indians was very much like what we breathe in today, with the exception of a large group of air contaminations presented in the course of the last 100 or 200 years. Head among these additional gases, or contaminations, are additional carbon dioxide and methane. Since around 1860, the development of the Industrial Revolution, carbon dioxide levels in the air have expanded in excess of 30% because of industrialization and deforestation. Methane levels have dramatically increased due to horticulture, land use and energy creation. The capacity of expanded measures of these gases to trap heat is the thing that drives worries about environmental change in the 21st century. See The Changing Climate, by Stephen H. Schneider. Scientific American, September 1989. The ice centers have shown that supported common paces of overall temperature change are ordinarily around 1 degree Celsius each 1,000 years. These movements are still significant enough to have profoundly adjusted where species reside and to have conceivably added to the annihilation of such alluring megafauna as mammoths and saber-toothed tigers. In any case, a most uncommon story from the ice centers isn't the general steadiness of the environment during the previous 10,000 years. Apparently, during the tallness of the last ice age 20,000 years prior, there was 50% less carbon dioxide and not exactly half as much methane noticeable all around than there has been during our age, the Holocene. This NDING proposes a positive input between carbon dioxide, methane and climatic change. The thinking that upholds the possibility of this destabilizing criticism framework goes as follows. At the point when the world was colder, there was less grouping of ozone-depleting substances, thus less warmth was caught. As Earth heated up, carbon dioxide and methane levels expanded, speeding up the warming. On the off chance that life took part in this story, it would have been to drive, instead of to go against, climatic change. It shows up progressively likely that when people turned out to be important for this cycle, they, as well, assisted with speeding up warming. Such warming has been particularly articulated since the mid-1800s in view of ozone-depleting substance emanations from industrialization, land use change and different marvels. By and by, however, vulnerabilities remain. By and by, most researchers would concur that life could well be the chief factor in the positive input between climatic change and ozone-harming substances. There was a fast ascent in normal worldwide surface temperature toward the finish of the 20th century. See delineation on inverse page. For sure, the time frame from the 1980s ahead has been the hottest of the previous 2,000 years. 19 of the 20 hottest years on record have happened since 1980, and the 12 hottest have all happened since 1990. The unsurpassed record high year was 1998, and 2002 and 2003 were in second and third places, separately. There is valid justification to accept that the time of the 1990s would have been much more smoking had not Mount Pinatubo emitted. This spring of gushing lava put sufficient residue into the high climate to obstruct some occurrence daylight, causing worldwide cooling of a couple of tenths of a degree for quite a while. Could the warming of the previous 140 years have happened normally? With truly expanding sureness, the appropriate response is no. The crate at the correct shows an exceptional report that endeavored to push back the Northern Hemisphere's temperature record an entire 1,000 years. Climatologist Michael Mann of the University of Virginia and his associates played out a complex measurable investigation including exactly 112 distinct variables identified with temperature, including tree rings, the degree of mountain glacial masses, changes in coral reefs, sunspot movement and volcanism. The subsequent temperature record is a remaking of what may have been acquired had thermometer-based estimations been accessible. Real temperature estimations are utilized for the years after 1860. As demonstrated by the certainty range, there is significant vulnerability in every time of this 1,000-year temperature remaking. Yet, the general pattern is clear: a steady temperature decline over the initial 900 years, trailed by a sharp temperature upswing in the 20th century. This chart recommends that the time of the 1990s was the hottest of the century as well as of the whole past 1,000 years. By considering the change from the high carbon dioxide, low oxygen environment of the Archean to the time of incredible developmental advancement about a large portion of a billion years prior, it turns out to be evident that life may have been a factor in the adjustment of environment. In another model, during the ice ages and interglacial cycles, life appears to have the contrary capacity, speeding up the change as opposed to lessening it. This perception has driven one of us, Schneider, to fight that environment and life co-evolved as opposed to life serving exclusively as a negative input on environment. On the off chance that we people view ourselves as a feature of life that is important for the common framework, at that point it very well may be contended that our aggregate effect on Earth implies we may have a significant co-transformative part later on for the planet. The latest things of populous development, the requests for expanded ways of life and the utilization of innovation and associations to accomplish these development-situated objectives all add to contamination. At the point when the cost of dirtying is low and the air is utilized as a free sewer, carbon dioxide, methane, chlorofluorocarbons, nitrous oxides, sulfur oxides and other toxics can develop. Extreme changes ahead. In their report Climate Change 2001, environment specialists on the Intergovernmental Panel on Climate Change assessed that the world will warm somewhere in the range of 1.4 and 5.8 degrees Celsius by 2100. The gentle finish of that range, a warming pace of 1.4 degrees Celsius each 100 years, is as yet multiple times quicker than the 1 degree Celsius each 1,000 years that verifiably has been the normal pace of characteristic change on a worldwide scale. Should the higher finish of the reach happen, at that point we could see paces of climatic change almost multiple times quicker than common normal conditions, which could prompt changes that many would think about perilous. Change in light of current circumstances would more likely than not power numerous species to endeavor to move their reaches, similarly as from the Ice Age, interglacial progress somewhere in the range of 10,000 and 15,000 years prior. In addition to the fact that species would need to react to climatic change at rates 14 to multiple times quicker, however few would have undisturbed, open relocation courses as they did toward the finish of the Ice Age and the beginning of the interglacial period. The negative impacts of this huge warming on well-being, agribusiness, waterfront geology and legacy destinations, to give some examples, could likewise be extreme. To make the basic projections of future climatic change expected to comprehend the destiny of environments on Earth, we should burrow through land, ocean and ice to gain as much from geologic, paleoclimatic and paleoecological records as we can. These records give the background against which to align the rough instruments we should use to look into a shadowy natural future, a future progressively annuanced by us.
If you enjoyed this video, be sure to give it a like and subscribe to Life is Often if you haven't already. Click the bell icon to stay updated on all our latest content.